Hello everyone, and welcome to today's chem lesson. Today, we are going to be talking about the point of balanced equations. Once we have an equation that is balanced, what do we use it for? What do we do with it? And here we have a visual that's going to help us out with that. A balanced equation, like we have up top here, gives us a lot of information. It gives us that information in a bunch of different ways, however we need to interpret it. The equation can talk about molecules, right? Saying that two molecules of hydrogen and one molecule of oxygen combine together in the right circumstances to make two molecules of water. Right? We see that here. Right? These are our H's. These are our O's. That's not gonna, I should have known that wasn't gonna work. These are our O's, and then we get our H2O over here. The balanced equation, these coefficients can represent numbers of molecules. They could also represent numbers of moles. Right? 2 moles of hydrogen molecules and 1 mole of oxygen molecules make 2 moles of water molecules. And then to go along with each of those scales, we can talk about mass. Mass at the atomic scale. 4 AMU's worth of hydrogen. Right? Remember taking the number from the upper left-hand corner of the cell of the periodic table. When we're talking about molecules, that number is in AMU. When we're talking about moles, this number is in grams. So, 4 AMU's worth of hydrogen and 32 AMU's worth of oxygen makes 36 AMU's worth of water. Or alternatively, take those AMU's and make them grams. Scale it up to talk about moles. 4 grams of water, 32 grams of oxygen, or 4 grams of hydrogen, 32 grams of oxygen make 36 grams of water. And when we look at it, we're trying to focus on the chemistry that is a little bit on the more practical side. We're trying to focus on things that we can actually manipulate, right? Looking at moles and grams rather than molecules and AMU. Because while it's nice to know this information, the molecule amount and the AMU amount, really, we can't do anything with that. We are not at a big university that has these tools. We're not in a fancy laboratory that has these tools. Right? We want to be able to make things work using grams and mole amounts because that is the practical application of chemistry here. And with that in mind, we're going to look at 3 different possible problem types. Using a balanced equation, we're going to look at converting moles to moles, right? Taking a known mole value and asking for an unknown mole. Taking a known mole amount and getting an unknown mass amount. A known mass amount and converting it to unknown moles. And then we're going to leave this one out because it's more on the AP level, but there is also the possibility of going from known mass to unknown mass. And we're going to look at them in terms of easiest up top down to most difficult. And do a couple of examples with each of these 3 things. And while this may seem daunting at first, it's really not quite so bad. It's the same as taking a recipe and adjusting it to feed more or less people. If I've got a recipe for 12 cookies, but I'm feeling like 24, I know what to do in that situation. We're going to double all the ingredients. we're going to do similar things, right? Similar concepts here. So let's take a look, right? The first one we're going to look at is, again, mole to mole calculations. Now, these are the simplest type, right? This is actually going to be a thing we do for everything moving forward. It's the basis of all stoichiometry. If you look at our example here, they give us an equation. Notice it is an unbalanced equation. And they ask us, if we react 1 mole of oxygen with unlimited hydrogen gas, how many moles of water will be produced? So, in order to solve this problem, we're going to do these 2 steps. We're going to balance the equation, make sure that our equation is properly balanced, and then we're going to use the mole ratio. And for this, I want to show you what I like to do as the easiest way to solve these kinds of problems. Now, you may have noticed I've always been putting these underlines when we started balancing equations. Right? Whenever I write out an equation, I've been putting these underneath. Right? When we balance this equation, right, it's the same one we saw in our example before. Right? It's 2 hydrogens, 1 oxygen, 2 water. Right? Just to double check ourselves, right, let's count. Right? That's 4 H's and 2 O's on the left. 2 waters is 2 times 2, 4 H's, 2 times 1, 2 O's. So we are balanced out. So that's our first step, right? Make sure we have a balanced equation. Now, we want to use the mole ratio. And this is where our little underlines come in. A ratio deals with fractions, right? So we are actually going to use these as if they were fractions, with these purple numbers in the numerator. Right? These are our known. This is our balanced equation in purple. And then we're going to switch over to blue for our problem. And those are going to go in our denominator spots. Now, when we are given a problem, there's one thing that we know and one thing that we need to find. The hydrogen in this case does not matter. It does not come into play here. And so we're going to leave it out. It does not make a difference. We're actually going to just put a light little X through it. We already used the hydrogen as much as we needed to balance this equation. But the problem wants to know about oxygen and water. And they say if we react 1 mole of oxygen, so we're going to put a 1 in the denominator here, how many moles of water will be produced? And now, I want these 2 fractions to be equal. Right? Using the mole ratio is figuring out these 2 fractions. 1 over 1 equals 2 over what? Right? In this case, our numerator and denominator are the same here for our oxygen, so they should be the same here. 2 over 2. And so a big 2 moles of water is going to be our answer. Now, what if they're not the same, right? What if this question has said 4 moles of oxygen gas? What if this was a 4? How do I solve out for this new H2O mole quantity? I've got 1 over 4 and I want that to be equal to 2 over something. Right? And depending on how you like to think about these, you can either look at the relationship here, right, between numerator and denominator, and apply that same relationship here to numerator and denominator. Right, saying 1 over 4, this is 4 times bigger, the denominator. So here, my denominator should also be 4 times bigger, so 2 over 8. Or, if that's not the way you immediately start thinking about these, you can look at the relationship between the numerators. This 1 became a 2. This doubled. So then this denominator should also double. So 1 became 2, 4 became 8. Either way, 8 is going to be the answer you end up with. But it depends on which way you like thinking about them. Right, that's our mole ratio. Right, that's how we use the mole ratios. We put the balanced equation up top, whether we have to solve for it or it is given to us. And then we focus on the things that the problem asks of us, and we look at the relationship between those. Something important to note is that these purple numbers, right, our balanced equation is always moles. Always, always, always. And that means our problem, the things we put underneath to use our mole ratio, should also be moles. Right, this only works if you use moles for your balanced equation and moles for your problem. When we go further and we look at things that contain mass, we're going to come back to this and say, okay, make sure it's in moles. Now, let's do some practice problems. Here we have 3 practice problems. Remember that your steps here are to balance the equation and then use your mole ratio. I'm going to put about 1.5 minutes on the clock. If you need more time, please, please, please just pause and keep working. But after that 1.5 minutes, I'm going to look at these answers. When we look at the answers to these questions, we're going to get these. Now, let's take a quick look at them together. This equation, this first equation, C plus O2 becomes CO2, starts off balanced. So it's a 1, and a 1 up top. The question says how many moles of carbon, so a question mark under our carbon for the denominator there, are needed to make 4 moles of carbon dioxide. So a 4 under our carbon dioxide. The oxygen doesn't play in here, so we're just going to leave it alone. 1 here became a 1 on the other side. So our 2 numerators are the same, which means our 2 denominators should be the same, making this a 4. Alternatively, if you look at the one we're given, this was multiplied by 4. 1 became 4, so times 4 going down. So this should be times 4 going down. But either way you slice it, you should get 4 moles of carbon. For the second one, the balanced equation is 1, 3, 4, and 5 over here. And so when they're asking you how many moles of oxygen, so question mark under this denominator, is going to react with 5 moles of C3H8, we're going to compare our 2 important pieces here, right? The carbon dioxide and the water get left out. They were important to balance the equation, but are no longer important for the question. If we look at the relationship between the numerators, I multiplied 1 times 5 to get 5. So I should multiply 5 times 5 to get 25. It's actually the same relationship if you look at the numerator to the denominator. Right? 1 to 5 is multiplied by 5. So here I should also multiply by 5 to get my 25. Either way you slice it, you're going to get 25. Now for this third problem. It's worded in a way that's a little bit different than we might have been used to. When we balance the equation, we get 2, 2, and 3. And here they're saying if we start with 2 moles of the reactant is anything, or reactants plural, is anything on the left side of the arrow. So here, KClO3 is our reactant. How many moles of each product? Product is anything on the right side of the arrow. How many moles of each product will be produced? So if we start with a 2 here, what goes under each of these? Right, these are the same, so we should end up with the same denominators here. Right, 2 over 2 moles of KCl, 3 over 3 moles of O2. And we get the same question, but now it's a 1. Right, if we start with 1 mole of the reactant, here I cut in half, right? 2 became 1, so that's half of what it was. So these should all be half of what they were. So a 1 and a 1.5. And while we never use decimals or fractions in our fully balanced equation, when we're solving a problem, 1.5 moles is a totally acceptable answer. It's never okay to balance the equation with it, but solving a problem, this is totally fine. Let's kick it up a notch here. Next up is a mole to mass calculation. We're going to use the first 2 steps are going to remain exactly the same. We're still going to balance the equation and use our mole ratio. But the third thing we're going to do here is convert to grams using the periodic table, using our mole calculations like we did in the past. So let's set up our problem again here. H2 plus some amount of O2 makes some amount of water. We're going to balance in purple again. 2, 1, and 2. Then we're going to solve out our problem. Solve out our problem in red. 3 moles of O2. So I'm going to put my 3 under here. How many grams of water will be produced? So I'm still looking at water. This is the denominator I care about. So, what number gets filled in for this question mark? Again, I can look at it one of two ways. I can look at the relationship between the numerators. 1 became a 2, so this doubled. So this, the denominators, 3 becomes a question mark, should also double. Meaning this should be a 6. Alternatively, I could look here, right? 1 became a 3, so this tripled. So 2 became a 6, so this tripled. Either way, you're going to get 6 here for your water. But is 6 the answer to my problem? Is it 6 grams of water? And this is where I'm going to remind you that all of these numbers are always moles. 2 moles of water, 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water, 3 moles of oxygen, 6 moles of water. That's not grams. Right? When we plug in numbers like this, these always are talking to us about moles. But we can figure out, we can take 6 moles of water and convert it to grams of water. We know how to do that. We know if we look at the reference table, we can pull up how much 1 mole of H and 1 mole of O weighs. So we know if we have H2O, which is an H, and an O, 116 for a total of 18 grams. We know what 1 mole of water weighs. And so if we have 6 moles of water, we can figure that out. Right? What's 6 times 18? Right, 6 moles times 18 grams per mole. Moles cancel out, leaving us with just grams and a wonderful number of 108. Nice. And so our answer here is not 6 moles of water. Our answer here is 108 grams of water. It's the same setup, right, as what we were doing before. We're still balancing and converting using our mole ratio, but now at the end we're also going to do a conversion using the masses on the periodic table to get grams of our mystery thing instead of moles of our mystery thing. That one added step is the convert to grams. So let's look at some practice problems here. Here, only one equation, and I'll remind you that when we balanced this last time, it looked like that. And the important values from the periodic table are going to be for H, which is a mass of 1, carbon, which has a mass of 12, and oxygen, which has a mass of 16. And so again here, I'm going to put about 1.5 minutes on the clock and let you try these out. When we look at our answers here, we're going to get something along the lines of this. And again, our balanced equation, right, just because it doesn't save my ink between slides, looks like this. And we get our H, C, and O values from the periodic table. Our first question says 1 mole of C3H8. So we're going to pull out just the important pieces here. Right, we're looking at C3H8 and carbon dioxide. So we're going to leave everything else out and just pull out the important bits from our balanced equation. 1 mole of C3H8 is going to give me how many moles of carbon dioxide. In this case, same numerator and denominator means same numerator and denominator. This should be a 3. But this is moles of carbon dioxide, not grams of carbon dioxide. And so we have to add up CO2, so C and O, 12 and 16 and 16, to give me 44 grams equals 1 mole. If 44 grams is 1 mole, 132 is 3 moles. For the second question, we are looking at C3H8 and water this time, so we're going to pull out the important bits of our equation. 5 moles of C3H8 is going to give me how many moles of water. Here we look at this relationship either across, right? So 1 to 4 is times 4. So this should be 5 times 4 to give me 20. Or I could look down, right? 1 became a 5, so multiplied by 5. 4 becomes a 20 if I multiply it by 5. But again, this is moles of water. I need grams of water, so I'm going to take H plus O, 1 plus 1 plus 16. 18 grams equals 1 mole of water. So 20 times 18 gives me my 360 grams of water. Now there's a trick to the third question, right? You can set it back up exactly the way that you set up the first one, right? Carbon dioxide, C3H8, use your ratio. Or if you look carefully, this and this, the first and third question, are almost exactly the same. Except I cut my amount of C3H8 in half. And if I cut this piece in half, I should just be able to cut my answer in half. Which you totally can. And it gives you the right answer. Right? You can also still set everything up exactly the same way. With your CO2, R3, this is a 0.5, which means when we look at our ratio here, we're going to get 1.5 moles of CO2. We know C plus O, 12 plus 16 plus 16, 44 grams is 1 mole. So 1.5 times 44 gives us our wonderful 66 grams. Now our last type of calculation that we're going to do here is actually the reverse. We're going to start with mass and go to mole. Here, again, we're going to be doing the same 3 steps. We're going to be doing them in a different order. It was 1, 2, 3 before, right? We balanced, we used the mole ratio, and then we converted. Here we're going to convert before we use the mole ratio, so we're just a little bit out of order. Same 3 steps, same process. We're going to start with our balanced equation. 2H2 plus 1O2 makes 2H2O. But here they give us 48 grams of oxygen, and I cannot just put that as my denominator, right? That's not a mole value. And so I need to convert first. So I know O2 is 16 and 16, 32. This is 1.5 moles. Right? If 1 mole of O2 is 32 grams, then 48 is 1.5 moles. So my 1.5 is what's going to go under here, meaning I'm going to get a 3 when I convert with my ratio, right? This doubled, so this doubled. This was times 1.5, so this should be times 1.5. Right? Either way you want to look at it. But now we already did our conversion, so this is our answer. Right? They're asking us for moles, and so we are giving them moles. It's the same set of steps, just in a different order. We're doing our conversion first from grams to moles so that we can plug numbers in to our mole ratio. Let's just jump in and give it a shot. Here you've got 2 problems. The first one says chlorine gas, sodium metal, and making salt. That's for question 1. And for question 2, you've got aluminum reacting with oxygen to make aluminum oxide. All right, try balancing them out, converting to moles, and then using your ratios. And these are the toughest 2 we're going to look at. here, our first step is to balance our equations. We're going to start with a 1, 2, 2 ratio for number 1. To balance the second one, we're going to need 2, 3, 1. No. Boop, 4, 3, 2. So once the equations are balanced, we can start looking at what they give us. The first one gives us 100 grams of chlorine gas. Chlorine is the only element that doesn't go to the nearest whole number. It goes to 35.5. So 1 mole of chlorine is going to be 71 grams. 100 grams of chlorine is going to be converted into 1.4 moles. How many moles of salt can I make with that? I look here, this doubled, so this should double. So 1.4 should be 2.8 moles of NaCl. You could also look down here, right, times 1.4 times 1.4, and you can take my word for it, plug it into a calculator. 2 times 1.4 gives you 2.8. Now our second one says that you have 300 grams of aluminum. And when we double check the periodic table for aluminum, aluminum has a mass of 27 grams per mole. And so we're going to take 300 divided by 27. To give us 11.11 moles of aluminum. We're trying to produce aluminum oxide here. And this is actually the first time we're seeing this happening. The ratio actually decreases. We went from 4 to 2. So this is half as much. So we should get half as much of our 11.11. So that's 5.55 moles of aluminum oxide. And again here, look, it's the same 3 steps, just in a different order. Instead of plugging in and looking at our ratio first and then converting, we're converting first and then looking at our ratio. And with that, I'm going to transition us over to our Zoom meeting for questions, comments. No, excuse me. Right at the end, I had to sneeze. For questions, comments, concerns, and attendance. And I will see you there.